My name's Abdullah, and I'm going to be talking to you guys about how neuroscientists use recurrent neural networks to model neuronal behavior. So we have to start with the question, what is a recurrent neural network? So you can imagine a recurrent neural network to be uh, almost exactly like, your usual neural network, except that it also takes in information um, on what it's done before. So for this example here, in a neural network, you would have this input xt. It would go into your network. You would produce some output, some classification or some hypothesis, and that'll be ht here. The additional arrow here, this recur, um, is information about the stuff that the network has done previously. So this is the additional stuff that makes a recurrent neural network recurrent instead of just a regular neural network. Now, how you can think about it is you can actually unroll the RNN in time. And so each of these would be the network doing some processing at a certain time point. So at time equals 0, it takes in this input x0, produces this output h0. At time equals 1, it takes in this input x1, produces h1, but it also takes in information from what was previously done in the last time step. And you'll see this continues for every next time step. So every time you give it information to try to produce some classification, some regression, some value, whatever, it's also remembering the stuff that it's done previously in previous time steps. Now, one way to think about this is you can kind of draw it out like this, where this is our recurrent neural network. It's 4 neurons wide. And so you put information into these 4 neurons and it produces some output, which we're not really looking at right now. But these neurons will send their information to the next time step. So this is the same network the next time you use it, and it's receiving information from the previous time it ran. And so there are all these weights between the time steps that we can kind of try to analyze to figure out how it's behaving. Now, as it turns out, analyzing the dynamics, the behavior of our networks by looking at this full set of weights is really hard. It's really complicated. It gets very complicated very quickly. And so what we like to do is what's called a low rank restriction. And it's this simplification. So we reduce the number of possible weights that exist by making sure that there's only one weight for every single neuron in this network. And this just makes it easier to figure out exactly what that network is doing. And you can think of it as kind of taking that set of weights and approximating it. Mathematically, it turns out that there is a full set of weights that correspond to whatever configuration you set here, whatever simpler configuration you've set here. Now, that is kind of the rundown on what a recurrent neural network is. Basically, yeah, it's just a neural network, except it has some amount of memory, kind of remembers what it's done before. Now, as it turns out, recurrent neural networks are decent approximations, make decent approximations for neuronal networks in your brain, at least very simple ones. And the question that these computational neuroscientists were wondering was whether neurons or neural networks should be analyzed through the lens of functional classes or mixed selectivity. What functional classes means is that every single neuron in a neuronal network belongs to a particular class and does a particular task for the computation at hand. With mixed selectivity, each neuron is a multi-tool. It can do a lot of different things, and it depends on the computation that's being done. And so to analyze the behavior of a network, you would want to look at what the whole network is doing at once. You wouldn't be looking at individual neurons because each individual neurons can do a variety of tasks. So it doesn't really matter what a particular neuron is doing. You just want to look at the behavior of the whole thing at once. Um, and to kind of try to glean some insight into this question, some neuroscientists decided to model some networks doing a particular task using recurrent neural nets, and then take a look and try to see if they could detect classes of neurons in those networks they've trained, or if the neurons seemed very mixed selective or a bit more randomly distributed. So the tasks that there were a variety of tasks that they used to train their networks. But the two that we're going to look at, the two important ones really, are this multi-sensory decision-making task, which is basically you're given two different input streams. If you have a mouse, it could be you're flashing something on screen and playing a sound on a speaker. And then the mouse has to decide whether it has heard a lot of sounds or seen a lot of lights, or if it hasn't heard or seen a lot of stuff. So it could be right means that it has seen or heard a lot, and left could mean it hasn't seen or heard much. And so it just makes a decision based off the combination of those two inputs. The context-dependent decision-making task is similar, and there are two types of inputs. So in this case, we're kind of looking at these set of colored dots. And we're asking the mouse or the subject to make a decision on whether the dots are moving to the left or the right, or whether the majority of the dots were colored green or red. And so these are the two different inputs. It's motion and color, and it's given both at once, but it has to make a decision on only a single input at each time. And these are the two tasks. So you can think of them with multi-sensory decision making. You are you're interpreting the two inputs at the same time together. And with context-dependent decision making, you have to figure out which input you want to pay attention to. Okay, now keep in mind the original question here is whether the neurons are, you know, the neurons belong to different classes or whether they're mixed selective and all kind of operate similarly. What we can do is we can kind of plot out all the weights and biases of our trained network on this graph. And we see kind of that for the multi-sensory decision-making task, for the one where you were interpreting both inputs at once, we kind of see this random distribution for the weights. For the contextual decision-making task, we see a little bit more structure. It's not very randomly scattered. It's forming like very specific shape. We can perform this E-pairs test, which tells us how random that random distribution is. And we see for the MDM task, it's pretty random, close to 0. And for the CDM task, it's a lot less random. So that kind of brings us to what exactly we mean by random distribution. And in reality, we're saying that this fits a Gaussian distribution. Some of you guys may have seen this before. This is the normal distribution. And basically, it means that you kind of have this average most likely value, and all your data points exist with the probability of this graph. So this U or this mu is the most likely value. And as you get farther away from mu, the likelihood that that number appears is less and less. And in 2 dimensions, it looks like basically what we saw for our MDM task. You have a concentrated set of points in the center, and there's fewer points as you get further away from the center. So taking a look at our RNNs, what we can do is we can try to apply we can try to fit a Gaussian distribution to them. And this is the same as trying to fit a linear regression to a set of points. So we can fit the Gaussian to it, and you can kind of see it looks like this little circle here. So we have this Gaussian fit to the multisensory, we have this Gaussian that we fit to the contextual. So after fitting the Gaussian, what we can then do is we can take some brand new networks and randomly pick points according to that distribution that we fit to the original data set. And what that means is we're not training these networks, we're just picking the weights and biases based off of the sampled, the distribution of the weights from our trained networks. So we can resample the weights. And what we find is that for the MDM task, the graph of those weights, of those weight vectors, they look very similar to the original for the trained one. The resampled and the trained look very similar. But for the contextual decision-making task, we seem to have lost some of the structure that we originally saw in the trained network. And if we look at the accuracy of the network for the tasks at hand, the MDM task has 100% accuracy. It works perfectly. But for the CDM task, it's only hitting 75% of the trained accuracy, which suggests that we've lost something after resampling. So what these scientists then did was they tried sampling that original CDM network, or tried fitting that network with two Gaussian distributions instead of just one. So the assumption being that there would be one distribution that would kind of fit over this set of neurons horizontally, and one that would fit across these neurons vertically. And they found that when they resampled according to two populations of neurons, you got near the trained network's accuracy versus one population which had a significant amount of accuracy loss. They took this a step further. So they took their trained network, and then they decided to try turning off the neurons that belong to one of the Gaussians. So if they fit two to them, they'll turn off one. And they found that, so if they took off population B, if they turned off the population B neurons, it did fine when having to pay attention to we'll call it data stream A, but when it tried to make a decision according to data stream B, the data stream B, it did much worse. And then the opposite occurred when turning off population A neurons. And if they just turned off random neurons instead of just choosing from a particular population that they worked out, the accuracy or the performance of the network didn't really change. There was enough redundancy that nothing really happened. So what can we conclude? From this particular thing, from this particular paper, we conclude that we should analyze a network by looking at the, whether we should analyze a network by looking at the overall behavior, assuming that all the neurons are mixed selective, or by trying to find functional subclasses of neurons. It depends very heavily on the task being done. Some of the tasks, like the contextual decision-making task, requires multiple classes of neurons, multiple tools to do the computation. Others are fine with fully random populations. And for a comprehensive analysis of a neuronal network, you need a combination of both approaches. Now, we keep in mind that this analysis was done with respect to these recurrent neural networks. So you would have to do further work to prove that this is the same case for organic neural networks. Although some of the work has been done by previous research showing that, these RNNs were good enough approximations for the simple tasks that they were studying.